It emerged from the vast expanse of space, utterly silent, frigid, and isolated. Yet, as it traversed the vicinity of our Sun, the celestial body designated 3 Atlas accomplished something unprecedented for any known comet. It increased its velocity. This acceleration was not a consequence of gravitational pull, nor was it propelled by gaseous emissions or the solar wind. Instead, it propelled itself. Recent data meticulously compiled by NASA serves as irrefutable confirmation of this phenomenon. An unseen force, one that eludes current understanding, exerted pressure on the object, counteracting the very force of gravity. Avi Loeb had presciently foreseen this precise moment months in advance. He theorizes that it could be a remnant, a fragment of extraterrestrial engineering, a dormant probe, or perhaps even a solar-powered sail passively drifting through the cosmos, navigating our solar system. Skeptics vehemently dismiss these notions as impossible, yet the empirical evidence cannot be refuted. Could this be the harbinger of our initial encounter with an alien intelligence? Not through overt communication, but through a subtle alteration in speed, a discreet salutation conveyed through mathematical precision. Remain with us until the conclusion, for the revelations that NASA has recently disclosed might well be the inaugural tangible indication that we are not solitary beings in this universe. If this enigma continues to hold you captive with anticipation, much like it has me, please ensure you register your engagement by liking this content and subscribing to our channel. This will guarantee you remain abreast of every development as this unfolding narrative progresses in real time. We encourage you to share your thoughts in the comments section below, indicating your current location, the local time, and your perspectives on this groundbreaking discovery. Furthermore, should you wish to contribute to the expansion of this inquisitive community, we invite you to disseminate this video across platforms such as X, Facebook, Reddit, or even within your personal group conversations. Your engagement is the driving force that empowers us to continue pursuing and uncovering stories of this magnitude. Therefore, our sincere gratitude for your unwavering support. Part 1. Breaking News. What if we have just detected the first technological imprint not originating from Earth, but from within interstellar space? What if, at this very instant, somewhere between the planets Mars and Jupiter, a fragment of alien craftsmanship is gliding through our solar system, and we nearly overlooked it? This is not a narrative from the realm of speculative fiction, nor is it a clandestine conspiracy theory whispered in the shadowy recesses of the Internet. This is substantiated by NASA's empirical data. This is grounded in the principles of orbital mechanics. This is a contemporary occurrence. And time is of the essence. On the dates of October 29th and 30th in the year 2025, an entity identified as 3 Atlas, marking the 3rd scientifically verified visitor from beyond our solar system, reached its closest proximity to the Sun. The scientific community denotes this celestial event as perihelion. For the vast majority of comets, the timing and trajectory of perihelion are precisely predictable. One calculates the intricate gravitational forces at play, accounts for the influence of the solar wind, and observes the object adhering to the fundamental laws of celestial motion, akin to a billiard ball traversing the expansive surface of spacetime. However, 3 Atlas deviated from this established paradigm. Instead, it demonstrably accelerated. This was not a marginal increase, nor was it within the acceptable margin of observational error. It accelerated in a manner that gravity alone cannot adequately explain. NASA's Jet Propulsion Laboratory, utilizing data procured from the Wide Field Imager 3 instrument aboard the Punch satellites, documented an extraordinary observation. The object underwent a radial acceleration directed away from the Sun of approximately 135 kilometers per day squared. Concurrently, it exhibited a transverse acceleration, perpendicular to its trajectory, of approximately 60 kilometers per day squared. While these numerical values may not immediately convey significant meaning, they represent a tangible force acting upon this object, entirely independent of the Sun's gravitational influence or the subtle push from any planetary body. Something else is propelling 3 Atlas, an agent unseen. Harvard astrophysicist Avi Loeb had foreseen this precise scenario months prior. Loeb, for those unfamiliar with his work, is the same astronomer who posited the theory that Oumuamua, the inaugural confirmed interstellar object discovered in 2017, might not be a natural celestial body, but rather a component of alien technology, possibly a light sail or a derelict probe drifting through the cosmos. This suggestion was met with considerable skepticism within the scientific community. It was decried as speculative, as an attempt to garner attention, and by some with even harsher criticism. Nevertheless, Loeb remained steadfast in his conviction. He maintained that humanity should maintain an open mind to extraordinary explanations when confronted with extraordinary data. And now, with the case of 3 Atlas, the evidence is becoming increasingly difficult to disregard. The anomalous acceleration is not the sole peculiarity. Consider its luminosity. 3 Atlas experienced a rapid increase in brightness as it approached the Sun, a characteristic not unusual for comets. However, the rate at which this luminosity intensified is highly atypical. Studies meticulously analyzing the object's photometry reveal a correlation between its brightness and its distance, following an inverse power law with an exponent of -7.5. This exponent is significantly steeper than that observed in typical comets, which generally brighten at rates closer to -2 to -4. In simpler terms, this signifies that 3 Atlas rapidly grew brighter, exceeding the predictive capabilities of our models for a simple chunk of ice and rock being warmed by solar radiation. Furthermore, there is the matter of its color. Comets are expected to scatter sunlight in a manner that renders them appearing reddish or neutral in hue, due to the presence of dust and organic molecules on their surfaces that absorb blue wavelengths. Conversely, 3 Atlas exhibits an unusually pronounced blue coloration. Loeb characterized this as highly unexpected. The blue light suggests the presence of either exceedingly fine particulate matter or something inherently reflective, perhaps metallic in nature, characteristics that deviate from the profile of a common icy body navigating the frigid void. Therefore, the central inquiry that is likely to occupy our thoughts for the foreseeable future is this: could 3 Atlas represent a fragment of extraterrestrial technology? Could it be a defunct probe, a component of a light sail, or perhaps even an operational spacecraft executing a gravity assist maneuver around our Sun? And if this indeed marks the moment we confirm our non-solitary existence, that intelligent civilizations have dispatched their creations across the galaxy, what implications will follow? This inquiry extends beyond the singular identity of this object. It fundamentally challenges our assumptions about what entities visit our solar system, our perceptions of the universe, and our understanding of humanity's position within it. Should 3 Atlas prove to be artificial in origin, then every comet, every asteroid, and indeed every piece of cosmic debris must be re-examined with suspicion. We will be compelled to confront the question of how many times we have encountered something anomalous and rationalized it away because the alternative was too unsettling. How many potential visitors have we failed to recognize because we were not prepared to perceive them? In the forthcoming segment, we will meticulously examine the raw data, delve into the scientific discourse, the prevailing controversies, and the official institutional responses. You will gain insight into the subsequent steps, the observational assets being employed, the planned investigations, and the potential revelations that may emerge. But first, it is imperative to establish the robustness of this assertion. We must scrutinize the precise measurements, the sophisticated instrumentation, the engineers who first identified the anomaly, and the scientists who are either championing or vehemently refuting it, because crucially, this situation is far from resolved. The scientific community is palpably divided. Some researchers are cautiously intrigued by the possibilities, while others remain vocally skeptical, and a select few are experiencing a profound sense of unease. This apprehension stems not from a belief that 3 Atlas is alien, but rather from the realization that if it is, humanity is wholly unprepared for the subsequent events. We currently lack established protocols for such a scenario. We possess no contingency plans. Our observational capabilities are barely aligned in the correct direction. Coming up next, we will delve into the methodology behind these measurements, explore the reasons why some scientists are labeling this the most perilous comet encounter that has never been publicly discussed, and investigate what evidence would definitively prove its artificial origin, crafted not by nature, but by intellects similar to, or perhaps profoundly unlike, our own, from some distant corner of the darkness. Part 2. Data and Source. Deep dive time, 0.5 seconds. The critical measurements that fundamentally altered our understanding originated from NASA's Punch satellite, more specifically, from an instrument identified as the Wide Field Imager 3. The acronym PUNCH stands for Polarimeter to Unify the Corona and Heliosphere, and its primary design objective was the study of the Sun's outer atmosphere and the resultant solar wind. It was not conceived with the intention of seeking extraterrestrial technology. Its purpose was to observe the outward propagation of plasma and magnetic fields emanating from our star. However, it is often the case that the most significant discoveries arise when instruments, fortuitously pointed in the correct direction at the opportune moment, are observing phenomena beyond their intended scope. David Finocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, undertook the detailed analysis of these captured images. Finocchia's expertise lies in orbital mechanics, the complex mathematics governing celestial trajectories, and the prediction of object positions based on gravitational and momentum principles. He meticulously superimposed images from the Punch satellite, tracking the movement of 3 Atlas frame by frame as it made its transit past the Sun. The patterns he observed were inconsistent with established predictions. The object was accelerating in a manner that could not be explained by purely gravitational forces. The radial component of this acceleration, directed away from the Sun, was measured at approximately 135 kilometers per day squared. The transverse component, acting perpendicular to the line connecting the Sun and the object, was approximately 60 kilometers per day squared. To provide context for these figures, a kilometer per day squared might seem negligible at first glance. However, over the span of a month, this acceleration compounds significantly. Loeb estimates that this non-gravitational force would cause the object's trajectory to deviate by roughly 10 Earth radii over a period of 30 days. This translates to a displacement of approximately 80,000 kilometers. In the field of orbital mechanics, this magnitude of deviation is considered exceptionally large. It represents the critical difference between a comet arriving at its predicted location and appearing entirely elsewhere, thus necessitating a complete reevaluation of all prior assumptions. The geometry of perihelion plays a crucial role in this context. On the 29th and 30th of October 2025, 3 Atlas reached its closest approach to the Sun, situated at an approximate distance of 1.36 astronomical units. This equates to roughly 203 million kilometers. For comparative reference, Earth maintains an orbital distance of 1 astronomical unit. Therefore, 3 Atlas passed the Sun at a distance marginally greater than Earth's orbital radius. This proximity was insufficient to cause vaporization, but it was close enough for the effects of solar heating to become significant. It was close enough for any volatile compounds, such as water ice, carbon dioxide ice, or methane, to begin sublimating if they were present. Herein lies a fundamental characteristic of comets. As they approach the Sun, they exhibit outgassing. Frozen materials on their surface absorb solar heat, transform into vapor, and are expelled outwards, creating the distinctive tails we associate with comets. This expulsion of gas generates a reactive force, akin to a rocket engine, which subtly alters the comet's trajectory. This phenomenon is termed the non-gravitational effect, and it is a well-documented aspect of cometary behavior. Astronomers routinely incorporate this effect into their calculations of comet orbits. However, the non-gravitational effect is intrinsically linked to the presence of observable gas and dust. It necessitates the formation of a coma, the diffuse envelope surrounding the nucleus. It requires spectroscopic signatures, emission lines indicative of water, carbon monoxide, and carbon dioxide, which confirm the comet is actively venting material. Crucially, 3 Atlas displayed acceleration without any readily apparent signs of outgassing. There were no discernible jets in the captured imagery, no prominent tail, and no spectral lines sufficiently intense to account for the magnitude of the observed acceleration. This is the anomaly that is currently fueling intense debate among scientists in academic forums and on social media platforms. Corroborating the trajectory data is the photometric analysis, the measurement of the object's brightness over time. A study titled Rapid Brightening of 3 Atlas Ahead of Perihelion, conducted by researchers including Zhang and Batams, meticulously documented the variations in the object's luminosity as it neared the Sun. Their findings indicated that the brightness correlated with distance, according to a power of -7.5. To comprehend the peculiarity of this observation, consider that most comets exhibit brightening rates closer to -2 to -4, dependent on the quantity of dust and gas they release. A steeper exponent signifies that the object is becoming brighter at a rate exceeding expectations, suggesting either the production of an unusual volume of reflective material or alterations in its surface, characteristics that are not readily explained. Spectroscopic observations provide an additional layer of complexity. Earlier in its approach, the James Webb Space Telescope detected the presence of carbon dioxide within 3 Atlas's coma, even when the object was still a considerable distance from the Sun. Carbon dioxide sublimes at lower temperatures than water ice, so its early detection is consistent with cometary behavior. However, as 3 Atlas drew nearer, the anticipated increase in water vapor, a characteristic signature of comets approaching perihelion, failed to manifest at the levels predicted. While some water was detected, its quantity was insufficient to explain the observed acceleration or the rapid intensification of brightness. NASA's own official documentation substantiates this timeline. The object reached its closest point to the Sun on October the 29th and 30th at approximately 1.4 astronomical units, aligning with the perihelion window reported by JPL. The photometry, the trajectory data, and the spectroscopy collectively lead to a singular conclusion. Something unusual is occurring, something that does not align with our current models of cometary behavior. It is important to acknowledge that models are, by their nature, approximations based on underlying assumptions. They presuppose specific compositions, surface properties, and thermal responses. When an object behaves contrary to these expectations, it does not automatically imply an artificial origin. It may simply indicate that our initial assumptions were flawed. This is the argument advanced by the skeptics, and it is a sound argument. Scientific progress is driven by the refinement of existing models, not by the immediate leap to extraordinary conclusions. Nevertheless, the degree of uncertainty remains significant. Astrometric fits, the mathematical process of aligning observed positions with predicted trajectories, inherently involve error margins. Variations in assumptions regarding the object's mass, its surface reflectivity, and its rotational rate all contribute to these calculations. Photometric interpretations are contingent upon how one models the dust-to-gas ratio, the distribution of particle sizes, and the surface albedo. Minor adjustments in these assumptions can lead to substantial shifts in interpretation. Consider the following analogy to illustrate this point. Imagine observing a vehicle traveling along a highway. You are aware of the speed limit and the engine's specifications. Based on established physics, you can calculate the vehicle's expected speed and its position at any given moment. Now, picture this vehicle commencing acceleration without the driver engaging the accelerator pedal. There is no apparent cause and no audible increase in engine RPM. The car simply accelerates. You consult your instruments and re-examine your assumptions. Perhaps there is an auxiliary motor at play, or the road is inclined, or a strong wind is influencing its motion. However, if you exhaust all plausible natural explanations and the vehicle continues to accelerate, you would inevitably begin to question whether an unaccounted-for factor is at play. This is precisely the juncture at which we find ourselves with 3 Atlas. The upcoming observational period scheduled for early November and mid-December of 2025 will either definitively resolve this enigma or dramatically escalate its mystery. Part 3. Loeb's interpretation versus natural hypothesis. The prevailing debate is dominated by 2 contrasting frameworks. On one side, the naturalistic explanation posits that outgassing and sublimation generate thrust, and that the emission of dust and gas accounts for the observed increase in brightness, with 3 Atlas representing an extreme manifestation of cometary behavior. On the opposing side stands the speculative hypothesis of an artificial origin, suggesting either radiation pressure acting upon a light sail, an internal propulsion mechanism, or an engineered structure designed for maneuverability through space. Both of these conceptual frameworks align with certain aspects of the available data. However, neither provides a complete and perfect explanation for all observed phenomena. Avi Loeb's reasoning is predicated on the concept of mass loss. If the observed acceleration is attributable to outgassing, meaning that sublimating ice is producing the propulsive effect that is altering the object's trajectory, then it is possible to calculate the requisite amount of mass the comet must be expending. The figures derived from this calculation are striking. To achieve an acceleration of 135 kilometers per day squared, a comet would necessitate the expulsion of a significant proportion of its total mass over a period of weeks or months. Loeb contends that such substantial mass loss should be readily detectable. It should manifest as a visible gas plume, a discernible tail, and robust spectral signatures that sophisticated instruments like the Hubble Space Telescope or the James Webb Space Telescope could easily identify. Yet these expected signatures have not been observed, at least not to the extent that would be required. While some carbon dioxide was detected at an earlier stage and some water vapor has been observed, the levels of emission are demonstrably insufficient to account for the observed acceleration. It is akin to witnessing a rocket launch without observing the accompanying exhaust plume. The effect is evident, but the causal agent is absent. Loeb further highlights the anomaly in the object's color. Comets scatter sunlight, and the dust they release typically absorbs blue wavelengths, resulting in the reflected light appearing reddish or neutral. However, 3 Atlas exhibits a distinctively blue hue. Loeb describes this as highly perplexing, as blue light typically suggests either the presence of extremely fine dust particles, significantly finer than those commonly found in cometary dust, or a reflective surface possessing characteristics more consistent with metallic or engineered materials. While natural processes can indeed produce fine dust, it is not a common occurrence, and certainly not in quantities sufficient to account for both the observed brightness and the unusual color. Consequently, what might an artificial origin entail? One plausible scenario involves a light sail. Light sails are constructed from exceptionally thin, reflective materials designed to be propelled by radiation pressure, which is the momentum transferred by photons emanating from a star. Scientists have proposed light sails as a potential method for propelling spacecraft across vast interstellar distances without the need for onboard fuel. A sail of sufficient size and minimal mass could, in principle, be accelerated by the force of sunlight. As the sail approaches a star, the intensity of radiation pressure would increase, thereby accelerating the sail further. In the vicinity of perihelion, this effect would be most pronounced, precisely replicating the radial acceleration observed in 3 Atlas. The mathematical calculations involved are intricate, but not insurmountable. The radiation pressure at 1.36 astronomical units is less intense than at Earth's orbital distance, yet it remains measurable. For a sail possessing an appropriate ratio of surface area to mass, exhibiting exceptional thinness and high reflectivity, it is theoretically possible to generate accelerations within the range of those that have been observed. The primary challenge lies in the fact that such a sail would need to be extraordinarily thin, possibly on the order of micrometers, and exceptionally reflective, with an albedo approaching 1. While this is achievable with manufactured materials, it is an unusual characteristic for natural celestial bodies. Another conceivable explanation involves an internal propulsion system. Envision a spacecraft executing a controlled engine burn at its point of closest approach to the Sun, utilizing the Sun's gravitational influence to amplify its velocity change. This is a standard maneuver within orbital mechanics, referred to as a powered gravity assist. Human spacecraft routinely employ such techniques. Engines are fired at the point of maximum proximity to maximize the efficiency of the thrust application. If 3 Atlas were such a spacecraft, it might be engaged in a maneuver deliberately designed to alter its trajectory for purposes that are currently beyond our comprehension. Loeb himself acknowledges this as speculative, and rightfully so. There is no direct evidence of an engine, no discernible thermal excess, and no observable exhaust plume. However, the absence of evidence does not equate to evidence of absence, particularly when the instruments employed were not specifically designed to detect such signatures in the first place. Loeb has also put forth the assertion that 3 Atlas represents the 9th anomaly associated with this object's observed behavior, suggesting it already possesses a documented list of unusual traits. He has been closely monitoring this celestial body, drawing parallels to Oumuamua, the first interstellar visitor, which also exhibited non-gravitational acceleration without any apparent outgassing. The similarities are compelling. Both objects are interstellar in origin. Both displayed anomalous motion. Both lack the unambiguous cometary characteristics that would be expected. A single data point may be an outlier. However, 2 data points begin to suggest a discernible pattern, and patterns, by their very nature, demand an explanation. Nevertheless, patterns can also be deceptive. Confirmation bias presents a genuine risk in scientific inquiry. When one is actively searching for evidence of extraterrestrial technology, it becomes facile to perceive it in every observation, even in data that might possess more conventional explanations. Critics of Loeb's methodology frequently highlight this very concern. They contend that he selectively chooses anomalies, disregards data that contradicts his hypothesis, and overemphasizes the improbability of naturalistic explanations. Consequently, the trajectory of future understanding hinges upon the observational data that will be acquired in November and December of 2025. Should these observations reveal substantial outgassing, should they detect water vapor and carbon monoxide in quantities sufficient to account for the observed acceleration, then the naturalistic explanation will prevail. 3 Atlas will be classified as an unusual comet, an extreme example, but ultimately a natural phenomenon. The case will be closed, and Loeb's speculative theories will recede into the background. However, if these forthcoming observations fail to detect adequate outgassing, if the acceleration persists without any discernible source, then the hypothesis of an artificial origin will become increasingly difficult to dismiss. It will transition from a fringe speculation to a credible possibility. At that juncture, the nature of the conversation will fundamentally shift. We will no longer be discussing comets and orbital mechanics in isolation. We will be contemplating the implications of contact, advanced technology, extraterrestrial intelligence, and what this signifies for humanity's place within the grand cosmic tapestry. Part 4: Controversy, Institutional Response, and Public Reaction. The scientific community is not a unified entity. This gathering comprises individuals possessing diverse training, varying perspectives, and differing thresholds for risk and speculative thought. When Avi proposes that an entity might be extraterrestrial in origin, some researchers perceive a visionary thinker pushing established boundaries. Others, however, view a scientist compromising scientific integrity for sensational headlines. Both interpretations hold validity and collectively influence the ongoing discourse surrounding the 3I Atlas anomaly. Mainstream scientists specializing in comets have adopted a cautious stance. Many contend that the collected data, while peculiar, does not yet warrant extraordinary pronouncements. Comets are inherently intricate. Their surfaces are a mosaic of disparate materials. Pockets of volatile substances can erupt sporadically, generating jets that do not align directly with the sun's emanations. These jets can exert rotational forces that modify spin rates, subsequently impacting how the comet reflects light and its acceleration. The simulation of these phenomena necessitates detailed assumptions, and these assumptions are inherently accompanied by uncertainties. The prevailing argument suggests that until all natural explanations are thoroughly explored, recourse to extraterrestrial technology should be withheld. This is a defensible position. Scientific inquiry is inherently conservative. Unconventional assertions demand exceptional validation, and the evidence indicating that 3I Atlas is artificial is not yet extraordinary. It is suggestive. It is intriguing. However, suggestive and intriguing fall short of being conclusive. Nevertheless, a distinct dimension to this debate exists, entirely unconnected to the observational data. It pertains to institutional conduct, openness, and public confidence. Loeb has publicly accused NASA of either delaying or withholding specific observations. To be precise, he asserts that an image captured by the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter on the 2nd day of October 2025 has not been disseminated. The high-rise instrument is capable of producing remarkably detailed imagery. Had it been directed at 3I Atlas during the object's approach, That image could contain pivotal information regarding the object's surface characteristics, its form, its reflectivity, and whether it exhibits any features incongruent with a naturally occurring comet. NASA has refrained from publicly addressing this particular assertion. This silence has fostered conjecture. On social media platforms, speculative theories have flourished. Some users posit that NASA is suppressing evidence under the assumption that the object is indeed artificial and that the agency wishes to avoid widespread public apprehension. Conversely, others propose that the delay stems from bureaucratic processes, asserting that image releases undergo standard review procedures, implying no sinister motive. The reality likely occupies a middle ground. Space agencies are wary of releasing data that might be misinterpreted. They are also circumspect about disseminating data before it has undergone appropriate calibration and verification. However, such prudence can be perceived as obfuscation, particularly when prominent scientists advocate for transparency. Further exacerbating the situation is NASA's public communication strategy. In late October, the acting administrator of NASA responded to an inquiry from a well-known Internet personality, reportedly Kim Kardashian, although accounts vary depending on the source, concerning whether 3I Atlas presented a threat or was of extraterrestrial origin. The administrator's reply was unequivocal. No extraterrestrials, no threat. While this statement aimed to assuage public concern, it had the contrary effect on certain segments of the audience. To critics, it sounded dismissive, as if NASA were downplaying legitimate scientific inquiries to sidestep controversy. This inherent tension between transparency and caution is not a novel phenomenon. Space agencies have perpetually navigated a delicate balance when dealing with anomalies that might suggest extraordinary origins. They aim to avoid fueling unfounded theories while simultaneously striving to avoid the appearance of concealing information. The challenge lies in the contemporary era of social media, where every decision is subject to intense scrutiny, every delay is questioned, and every statement is meticulously dissected for underlying significance. The International Asteroid Warning Network, a consortium of space agencies and astronomical observatories, initiated a comet observation campaign in response to 3I Atlas. This campaign, running from November 2025 through January 2026, is designed to synchronize observations from numerous telescopes and instruments, pooling data to achieve the clearest possible understanding of the object's nature and behavior. On the surface, this appears to be standard scientific protocol: an unusual object, a coordinated response, and rigorous analysis. However, some interpret the activation of this campaign as evidence that the agencies are treating the anomaly with significant seriousness, perhaps more so than they are publicly willing to acknowledge. Why initiate a coordinated campaign for a comet, unless one believes there is something meriting investigation? Why involve such a multitude of telescopes unless the stakes are elevated beyond routine observation? Public perception has undergone a rapid transformation. Prior to October, 3I Atlas was a peripheral concern within the astronomical community, one of several interstellar objects detected in recent years. It has now become a cultural touchstone, trending on social media and discussed in podcasts, YouTube videos, and journalistic articles. People are posing profound questions. Are we alone? Is this a pivotal moment of change? Can we place our trust in NASA? The latter question carries the greatest weight. Trust in established institutions is inherently fragile. When individuals perceive that information is being managed or deliberately withheld, they tend to fill the void with speculation, which can then escalate into a deficit of trust. Scientists like Loeb, who are willing to openly challenge institutional narratives, become polarizing figures. They are lauded by some as truth-tellers and criticized by others as attention seekers. The reality, as is often the case, is more intricate. What transpires if the evidence increasingly points towards an artificial origin? This is a scenario that no one wishes to discuss openly, yet everyone contemplates privately. If 3i Atlas proves to be a manifestation of alien technology, the ramifications would be immense. Policymakers would undoubtedly become involved. Oversight mechanisms akin to SETI, Search for Extraterrestrial Intelligence, protocols might be activated. Governments would inevitably pose critical questions. Is it a probe? Is it operational? Does it pose a threat? Or does it represent an opportunity? And should such a scenario unfold, the current discussions concerning comets and orbital mechanics would appear quaint in hindsight. Part 5 focuses on the immediate stakes and forthcoming observations. The temporal framework for the ensuing months is crucial. All subsequent developments hinge on observations scheduled for November and December 2025. These are not perfunctory follow-up studies. Rather, they represent targeted campaigns involving some of humanity's most advanced telescopes and instruments. The findings will either definitively resolve the 3i Atlas case or broaden its scope to an extent for which few are prepared. The European Space Agency's JUICE mission is slated to be the first observer. JUICE, an acronym for Jupiter Icy Moons Explorer, is presently en route to Jupiter, where its mission will involve studying Europa, Ganymede, and Callisto. However, orbital trajectories can lead to unexpected encounters. In early November 2025, JUICE is projected to pass in relatively close proximity to 3i Atlas. According to orbital calculations, the flyby distance will be approximately 0.428 astronomical units, or roughly 64 million kilometers. While not intimate in human terms, in the vastness of space, this is considered a near miss. JUICE is equipped with cameras and spectrometers. Should the geometry of the flyby prove advantageous, it could capture images of 3i Atlas with a resolution surpassing any obtained thus far. It possesses the capability to analyze the spectrum of reflected sunlight, searching for indicators of specific molecules or materials. If 3i Atlas is emitting gases, JUICE might detect these emissions. Should the object exhibit unusual surface features, such as facets, structures, or reflective patches, JUICE could potentially observe them. Avi Loeb has been vocal regarding the significance of the JUICE observations. He has posited that if 3i Atlas is a naturally occurring comet, JUICE ought to detect unambiguous signs of gas emission, including water vapor, carbon monoxide, and possibly ammonia or methanol. If these signatures are present in quantities sufficient to account for the observed acceleration, the natural explanation would be vindicated. Conversely, if they are absent or too weak, the hypothesis of an artificial origin would gain greater credence. Later in December, around the 19th, both the Hubble Space Telescope and the James Webb Space Telescope are scheduled to conduct observations of 3i Atlas. Hubble excels at capturing images across visible and ultraviolet wavelengths, making it ideal for detecting gas emission lines and quantifying how light scatters off the object's surface. JWST operates in the infrared spectrum, perfectly suited for detecting thermal emissions and identifying heat signatures that might suggest internal activity or anomalous surface properties. These forthcoming observations are expected to be more sensitive than any preceding them. If there is gaseous material surrounding 3i Atlas, Hubble and JWST will undoubtedly detect it. If there is dust, they will meticulously measure its composition and particle size distribution. Should thermal anomalies, such as hotspots, cold spots, or asymmetries be present, they will be precisely mapped. The resultant data will be subjected to analysis by multiple independent research teams, ensuring that no single interpretation gains undue dominance without rigorous examination. Terrestrial observatories are also participating in this coordinated effort. Telescopes situated in Chile, Hawaii, and the Canary Islands are integral components of the campaign. Spectroscopic observations will track variations in the object's light over time, searching for periodic fluctuations that could indicate rotation or surface features moving into and out of view. Photometric monitoring will quantify changes in brightness, thereby refining models of how the object reflects solar illumination. The potential outcomes can be broadly categorized into two scenarios. Scenario A posits that the observations detect sufficient outgassing and dust production to account for both the observed acceleration and the brightness anomaly. In this context, 3I Atlas would be definitively classified as a natural comet, albeit one exhibiting unusual characteristics. Scientists would subsequently publish research papers detailing its composition, its activity patterns, and the factors distinguishing it from other comets. The entire episode would then be relegated to a historical footnote in the study of interstellar objects, deemed interesting and instructive, but ultimately not revolutionary. Scenario B proposes that the observations fail to identify adequate gas or dust levels to explain the acceleration. The object would continue to accelerate without an apparent source of propulsion. Spectroscopic analysis would reveal surface properties inconsistent with those typically observed in comets. Thermal imaging would indicate anomalies. Under this scenario, the hypothesis of artificial origin would transition from speculative conjecture to a plausible explanation. Scientists would begin posing more challenging questions. Mission proposals would be drafted, and SETI researchers would become actively involved. Policymakers would be briefed on the findings. Should Scenario B materialize, subsequent actions could involve the deployment of targeted missions. Proposals might be fast-tracked to develop spacecraft capable of intercepting 3I Atlas while it remains within accessible range. A flyby mission could acquire close-up imagery, ascertain the object's mass and density, and conduct a detailed analysis of its surface. A rendezvous mission would involve orbiting the object, allowing for weeks or months of intensive study. If the object is indeed artificial, such missions would represent some of the most scientifically significant undertakings in human history. Furthermore, the implications for public perception warrant consideration. If evidence increasingly supports an artificial origin, public trust in established institutions will face significant tests. Individuals will demand answers, seeking to understand what governments knew when they acquired that knowledge and why the information was either shared or withheld. The media would undoubtedly amplify the narrative. Social media platforms would become inundated with theories, debates, and calls for greater openness. This juncture represents a critical turning point for contemporary astronomy. For decades, humanity has actively searched for indications of intelligent life beyond Earth. Radio telescopes have been directed towards the stars, diligently listening for signals. Exoplanet atmospheres have been meticulously analyzed for biosignatures. Frameworks have been established for detecting technosignatures encompassing megastructures, Dyson spheres, laser pulses, and any phenomena that might suggest the presence of advanced civilizations. However, there has been an underlying assumption that any such discovery would be distant, measured in light years, and therefore abstract and relatively safe. 3I Atlas diverges from this paradigm. It is not remote. It is within our solar system, close enough for direct study, within reach for potential exploration, and close enough to compel us to confront the possibility that we are not alone, and that the evidence has been drifting past us all along, awaiting the scrutiny of an observer. The coming months will determine whether this is indeed the case. Either we will conclude the Three-Eye Atlas investigation and revert to conventional scientific pursuits, or we will inaugurate a new era in human history, one where the cosmos is no longer perceived as vacant, but rather teeming with intelligence and technology, posing questions we are only beginning to formulate. And now we have examined the assertion, the supporting data, and the potential ramifications. Next, we will delve deeper into hidden trajectories, perplexing brightness variations, alleged conspiracies, the underlying physics, and hypothetical scenarios that challenge the limits of our perceived possibilities. Part 6 examines the trajectory and kinematic context. To comprehend the origin of Three-Eye Atlas, one must first understand the nature of interstellar space. The galaxy is not an empty void. Between the stars exist vast clouds of gas and dust, rogue planets, expelled comets, and debris resulting from stellar collisions. Objects traverse this interstellar medium for eons, moving under the gravitational influence of distant stars, their paths shaped by the gradual dynamics of galactic evolution. The majority of these celestial bodies will never approach another star, instead wandering perpetually in darkness. However, on occasion, one will venture sufficiently close to a star like our Sun to be temporarily ensnared by its gravitational pull, traversing the solar system on a hyperbolic trajectory before re-emerging into the void. Three-Eye Atlas represents the third confirmed object of this kind. The first was Oumuamua, identified in 2017. The second was Comet Borisov, discovered in 2019. Both were unequivocally classified as interstellar due to their hyperbolic orbits, indicating velocities exceeding the solar system's escape velocity. They were not gravitationally bound to the Sun, but were merely passing through. Population models suggest that interstellar objects of this nature are prevalent. A research paper by Hopkins and Dorsey, titled "From a Different Star," estimated that at any given moment, thousands of interstellar objects likely reside within Neptune's orbit. Most are too diminutive or too faint to be detected by current telescopic capabilities. This implies that we are not observing rare visitors, but rather the most conspicuous examples of a phenomenon occurring continuously all around us, largely unnoticed. Three-Eye Atlas possesses a velocity at infinity, its speed independent of the Sun's gravitational influence, estimated at approximately 20 to 30 kilometers per second, contingent upon the precise orbital solution. While this is a significant speed by solar system standards, it is typical for interstellar objects. Its orbital inclination, the angle of its path relative to the solar system's plane, is notably high, around 70 to 80 degrees. This is another characteristic indicative of an interstellar origin. Objects within the solar system generally orbit on a similar plane, having formed from the same protoplanetary disk. Interstellar objects, conversely, originate from random directions, their inclinations reflecting the chaotic nature of galactic dynamics. Pinpointing its precise origin is more challenging. While one can trace its trajectory backward, accounting for the Sun's gravity and the gravitational pull of the planets, uncertainties escalate significantly when extending the path into interstellar space. Minor inaccuracies in measured velocity or position compound over time. Nevertheless, researchers have attempted such calculations. Some models suggest Three-Eye Atlas originated in the thin disk of the Milky Way, the region housing the majority of stars and planetary systems. Others propose the thick disk, an older, more dispersed stellar population with distinct kinematic properties. The thick disk hypothesis is particularly intriguing, as it implies the object could be billions of years old, a relic from an earlier stage of galactic development. Could it have encountered other stellar systems? Almost certainly. Over billions of years, an object drifting through the galaxy will pass through numerous stellar neighborhoods, coming within a few light years of dozens or even hundreds of stars. Each such encounter subtly alters its trajectory. Over extended periods, the original orbit becomes erased, supplanted by a path shaped by countless gravitational perturbations. If 3I Atlas is artificial, this historical trajectory raises pertinent questions. Was it intentionally dispatched? Did it originate from a star that we can identify? Or has it been traversing space for such an extended duration that its origin is now obscured? The matter of spacecraft also arises. Humanity has dispatched several probes into interstellar space or on trajectories destined to eventually leave the solar system: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons. All of these spacecraft are traveling at speeds lower than that of 3I Atlas. If 3I Atlas is artificial, its velocity surpasses that of any technology we have developed, suggesting either a more advanced propulsion system or a prolonged period of acceleration, perhaps utilizing a light sail propelled by starlight over centuries or millennia. The JUICE flyby in early November introduces an additional element of interest. JUICE is traversing space en route to Jupiter, and its trajectory coincidentally brings it into relatively close proximity with 3I Atlas. Relatively close, of course, is a subjective measure. A distance of 0.428 astronomical units equates to approximately 64 million kilometers. This distance is far too great for detailed imaging by JUICE's cameras, but it is sufficiently close for spectroscopic analysis, provided the geometrical alignment and timing are favorable. JUICE was not designed to study interstellar objects, but serendipity occasionally presents opportunities, and this is one such instance. If 3I Atlas passes through regions characterized by unique plasma or magnetic field environments, these conditions could also prove significant. The solar wind, a stream of charged particles emanating from the sun, interacts with any object in its path. If the object possesses a magnetic field or a charged surface, this interaction can generate detectable signatures. If 3I Atlas is artificial, perhaps a spacecraft constructed from conductive materials, the solar wind might create a wake or disturbance that differs from that expected for a natural comet. Furthermore, the trajectory's proximity to other spacecraft is relevant. For instance, Mars orbiters have previously imaged comets. The Mars Reconnaissance Orbiter, equipped with its high-rise camera, is capable of extraordinary resolution. If it were directed at 3I Atlas during the object's approach, it could have captured details imperceptible to ground-based telescopes. The existence of such an image and its subsequent release are central to the ongoing controversy. The orbital path of 3I Atlas also has implications for future observations. As the object recedes from the sun, its apparent brightness will diminish. The intensity of reflected sunlight decreases with distance, and eventually, even the most powerful telescopes will struggle to detect it. This means the window for observation is rapidly closing. If the necessary information is not acquired in the coming months, the object will drift beyond our observational reach, fading into obscurity. However, here lies a speculative frontier. If 3I Atlas is artificial, perhaps dispatched from a thick-disk exoplanet system billions of years ago, then its passage through our solar system might not be a random event. It could be one of many such occurrences. We might be observing a single data point within a much larger pattern, a pattern that will only become discernible once we have detected a sufficient number of interstellar objects to discern statistical trends in their distribution, trajectories, and characteristics, indicative of deliberate voyages rather than random drift. This contemplation leads to a question that warrants serious consideration. How many such objects have we overlooked? How many have traversed the inner solar system before we possessed the necessary telescopic capabilities to detect them? How many are currently present, too faint or too distant for detection, potentially carrying information, advanced technology, or simply drifting as silent testaments to long-extinct civilizations? The trajectory of Three-Eye Atlas is more than just a line through space. It is a thread connecting us to the profound possibility that the galaxy is not silent or empty, but teeming with travelers similar to this one, and we are only now beginning to learn how to perceive them. Part 7 addresses the power law of brightness, anomalies, and photometric details. Numbers possess the ability to convey narratives, provided one possesses the knowledge to interpret them. The observed brightness of Three-Eye Atlas adheres to a power-law relationship. Specifically, its brightness is inversely proportional to the distance raised to the power of -7.5. Mathematically speaking, the brightness is directly proportional to a constant multiplied by the distance raised to the power of -7.5. For those less familiar with mathematical expressions, this essentially means that as the celestial body draws nearer to the Sun, its luminosity increases at a rate far exceeding what one would typically anticipate from a common comet. While most comets do become more luminous as they approach the Sun, their brightening typically follows a gentler pattern, usually governed by an exponent ranging between -2 and -4. An exponent of -2 signifies that the brightness escalates with the square of the diminishing distance. Conversely, an exponent of -7.5 implies that the brightness surges with nearly the eighth power of the decreasing distance. This disparity is not minor. It represents a substantial and remarkable difference, the kind that compels astronomers to pause and investigate, asking, "What is occurring here?" Several physical phenomena could account for such extraordinarily steep luminosity increases. One plausible explanation involves extremely fine dust particles. When sunlight interacts with particles, the effectiveness of light scattering is contingent upon the size of those particles. Smaller particles refract light differently compared to larger ones. If 3-second Atlas is generating exceedingly fine dust, with particles measured in micrometers rather than millimeters, this could contribute to a more rapid increase in brightness than standard theoretical models predict. However, the generation of fine dust typically necessitates processes like fragmentation, collisions, or sublimation, which break down larger particles into smaller fragments. These processes generally occur when a comet is highly active, expelling significant volumes of gas and dust. Yet, 30 Atlas does not exhibit the expected gaseous signatures indicative of such high activity levels. Another potential explanation is the rapid sublimation of volatile compounds. Carbon dioxide ice undergoes sublimation at lower temperatures than water ice. Consequently, as a comet approaches the Sun, carbon dioxide can begin to escape before water does. If 3-through Atlas is particularly rich in carbon dioxide, or if it contains other volatile substances like carbon monoxide or methane, these materials could be the driving force behind the observed increase in brightness. Initial observations conducted with the James Webb Space Telescope did detect carbon dioxide within the coma when the object was at a greater distance from the Sun, lending support to this hypothesis. Nevertheless, the quantity of gas detected still appears insufficient to fully explain both the observed brightness curve and the object's acceleration. Furthermore, there is the phenomenon of thermal fracturing. As a comet warms up, thermal stress can cause its surface to crack, exposing fresh ice beneath. This newly exposed ice is more reflective than aged or weathered ice, meaning that the revelation of new material could trigger an abrupt surge in brightness. This particular mechanism has been documented in other comets, especially those possessing layered or heterogeneous surfaces. However, thermal fracturing typically results in transient brightness spikes. The object experiences a sudden increase in luminosity, followed by stabilization or dimming as the freshly exposed ice gradually sublimates. The luminosity pattern observed for 3 Atlas appears more consistent with a continuous process rather than a singular event. Then there is the more speculative possibility of internal heating or controlled reflectivity. Should 3 Atlas possess an internal energy source, something generating heat from within, such as a decaying power source or an active engine, this could warm its surface in ways that deviate from solar heating alone. Alternatively, if the object features a surface with unusual reflective properties, perhaps engineered to amplify or diminish light reflection at specific wavelengths, this could produce a brightness curve that diverges from natural models. A comparison of 3 Atlas with other interstellar objects provides valuable insights. The first known interstellar visitor, Oumuamua, displayed no visible coma or tail, nor any apparent signs of outgassing. Despite this, it exhibited non-gravitational acceleration, leading to suggestions by Avi Loeb and others that it might be a solar sail or a component thereof. Comet Borisov, the second interstellar object detected, behaved in a manner much more akin to a typical comet. It possessed a discernible coma, a tail, and spectroscopic characteristics consistent with water and carbon monoxide. Its brightness increased as it neared the Sun, but its luminosity curve adhered to more conventional exponential relationships. 36. Atlas occupies an intermediate position between these two examples. It shows some evidence of gas and activity, yet not to a degree that fully accounts for its acceleration or its rapid brightening. It is anomalous, but not entirely alien, at least not definitively so. Color indices introduce another layer to the enigma. Photometry not only measures brightness, but also quantifies it across various wavelengths. By comparing an object's luminosity in blue light versus red light, astronomers can deduce properties about its surface or its composition of dust. Standard comets typically exhibit slightly reddish color indices because their dust tends to scatter longer wavelengths more effectively. However, 3 Atlas presents an unusually blue hue. A blue color suggests either the presence of very small particles, which scatter blue light efficiently, or a highly reflective surface with a significant albedo in the blue portion of the spectrum. Observations from the Subaru telescope and the Trident instrument, among others, have measured color magnitude differences, confirming this blue coloration. While not impossible for a natural comet, it is certainly uncommon. When the blue color is considered alongside the steep luminosity curve and the absence of pronounced gas emissions, it becomes clearer why certain scientists are intrigued while others remain skeptical. Each individual anomaly might possess a natural explanation. However, when they occur together, they form a pattern that is more challenging to dismiss. Recent scientific papers submitted to Archive, a repository for preprint scientific research, include measurements of water production rates at distances greater than 3 astronomical units. Water typically sublimates at temperatures corresponding to proximity to the Sun. Therefore, detecting water at an early stage suggests either highly efficient heating or the presence of exposed pockets of volatile, rich material on the surface. However, the measured rates of water production, while noteworthy, are not substantial enough to account for the acceleration observed near perihelion. This discrepancy between expected and observed behavior lies at the core of the mystery. Here, speculation becomes nearly irresistible. What if the surge in brightness is not attributable to dust or gas, but rather to the exposure of metallic surfaces? If through Atlas is a fragment of artificial origin, perhaps a damaged sail, a non-functional probe, or debris from an ancient collision, it might incorporate reflective materials that do not behave like ice or rock. Metals, particularly those with polished or engineered surfaces, possess high albedos and reflect light in ways that are dependent on the angle of incidence and the wavelength of the light. An object rotating erratically with metallic facets could generate brightness variations that do not align with cometary models. Alternatively, consider the possibility of internal illumination. This represents the most far-fetched speculation, but if third Atlas harbors an internal energy source, perhaps still partially functional after millions or billions of years of travel, this energy could manifest as heat or light. A spacecraft with a decaying power supply might emit infrared radiation detectable by instruments like the James Webb Space Telescope. A probe with failing systems could exhibit hotspots where electronic components are still drawing power. These are not hypotheses one readily proposes in a peer-reviewed journal, but they are ideas that surface during late-night contemplation when the collected data stubbornly refuses to conform to established models. The anomalies in brightness are not definitive proof of anything. They are clues. They are the breadcrumbs leading deeper into the unknown, prompting the question of whether one is following a path toward discovery or becoming lost in a labyrinth of coincidences. Part 8. Conspiracies, Data Transparency, and Biases. What if the reason for our surprise regarding through Atlas stems not from the object itself being surprising, but from our not having access to all the pertinent data? What if certain images, spectral analyses, or measurements are stored on servers somewhere, having undergone review by a select group of scientists, but have been withheld from public release for reasons ranging from bureaucratic necessity to more sinister motives, depending on one's perspective? Avi Loeb has publicly stated that NASA withheld imagery from the Mars Reconnaissance Orbiter. Specifically, he claims that HiRISE, the high-resolution camera aboard the orbiter, captured an image of 33rd Atlas on October 2, 2025, and that this image has not been made public. HiRISE is one of the most powerful cameras in orbit, capable of discerning features as small as 1 meter across on the Martian surface. If directed at an interstellar object, it could reveal details imperceptible to ground-based telescopes, such as surface texture, shape, and potentially even structures or features that would definitively answer the question of its natural versus artificial origin. Why would such an image be withheld? Several explanations are possible, spanning a spectrum from the mundane to the conspiratorial. The mundane explanation is that the release of images undergoes standard calibration and review processes. Raw data from spacecraft instruments is not immediately published. It is processed, checked for errors, calibrated against known standards, and reviewed by scientific teams prior to dissemination. This procedure can take weeks or months. It is not a cover-up. It is standard operational protocol. A less mundane explanation suggests that the image contains something controversial, something requiring careful interpretation before public disclosure. If the image reveals anomalies, features that do not align with the expected profile of a comet, NASA might delay its release until these anomalies are understood, thereby avoiding the fueling of speculation or misinterpretation. This is not necessarily malicious. Space agencies have encountered situations where releasing data prematurely led to misinterpretations by the public or media, fostering false narratives that are difficult to rectify once established. The conspiratorial explanation posits that NASA is aware of third Atlas being artificial and is deliberately managing the narrative to prevent public panic or societal disruption. This explanation is popular in certain online communities but is also the least probable. Space agencies are not monolithic entities. They comprise thousands of scientists, engineers, and administrative personnel, many of whom would likely not participate in suppressing evidence of extraterrestrial technology. Leaks would be virtually inevitable. Moreover, the scientific community operates on principles of transparency and peer review. Withholding data fundamentally undermines these principles and puts careers at risk. It is difficult to envision a scenario where such a conspiracy could be successfully maintained. Nevertheless, the perception of data withholding can be almost as damaging as the act itself. When scientists, such as Loeb, publicly advocate for transparency and do not receive clear responses, it erodes trust. People begin to question, what are they hiding? Why aren't they showing us everything? Once these questions take root, they are remarkably difficult to dislodge. The network announced a Comet campaign scheduled to run from November 2025 through January 2026. ION is a consortium of space agencies and observatories established to coordinate responses to potentially hazardous asteroids and comets. Initiating a campaign for 3-2 Atlas is logical if the object is sufficiently unusual to warrant coordinated observation. However, it also raises concerns. Is this merely standard protocol for an anomalous interstellar object, or does it signify that agencies are more apprehensive than they outwardly acknowledge? Institutional motivations play a role in this dynamic. Space agencies rely on public trust and government funding. If they prematurely speculate about extraterrestrial technology and are proven incorrect, they risk jeopardizing their credibility. Politicians might question the allocation of funds. The media could portray them as reckless. Conversely, if they are overly conservative and cautious in acknowledging anomalies, they risk accusations of concealing information or dismissing important questions. It is a delicate balancing act, and 3-2 Atlas is testing their equilibrium. Peer review and scientific caution are essential, but they can also function as barriers. When an idea challenges the prevailing scientific consensus, it undergoes heightened scrutiny, which is appropriate. Extraordinary claims necessitate extraordinary evidence. However, there is a risk that conservatism becomes ingrained, leading to anomalies being explained away, not due to the validity of the explanations, but because the alternative possibilities are uncomfortable. Confirmation bias can operate in both directions. One can be predisposed to perceive extraterrestrial involvement everywhere, or conversely, be predisposed to never see it, even when it is overtly present. Some experts in mainstream cometary and orbital dynamics have voiced criticism of Loeb's approach. They contend that he is selectively highlighting anomalies, focusing on data points that support his hypothesis while disregarding others that do not. They emphasize that cometary activity is inherently complex, that models are subject to uncertainties, and that rushing to artificial explanations before thoroughly exploring natural ones is premature. These are valid criticisms. Scientific progress is achieved through rigorous hypothesis testing, not through hasty conclusions. However, there is also the question of what constitutes a thorough exploration of natural explanations. How many models must be considered before alternative possibilities are entertained? How weak do the natural explanations need to be before speculation becomes justifiable? There is no definitive answer, and it is within this ambiguity that the controversy resides. Speculation concerning internal memos and unpublished data is inevitable. Perhaps there are higher-resolution images that have not been released. Possibly there are spectroscopic observations revealing unexpected features. It's conceivable there are internal discussions among scientists weighing how to present findings without causing misinterpretation. Or perhaps there is nothing to these suspicions, no conspiracy, No hidden data, only the gradual progression of the scientific process and the inherent delays associated with bureaucracy and peer review. The grainy appearance of released images from Punch has also been a subject of scrutiny. Is the graininess a result of the instrument's limited resolution, or was it a deliberate choice to release lower quality versions? The former is the more probable explanation. Punch's wide-field imager was designed to study the Sun's corona, not faint interstellar objects. Imaging through True Atlas pushed the instrument to its operational limits. The graininess is likely a reflection of these limitations rather than intentional obfuscation. Transparency in science is paramount, but it is also a complex process. Scientists work with incomplete data, uncertain models, and face pressure to be both rigorous and timely. When anomalies emerge, the inclination to speculate is strong, but so is the risk of error. Institutions strive to balance these competing pressures, but achieving equilibrium is challenging. In the current era of social media, every decision is subject to scrutiny, every delay is questioned, and every statement is analyzed for hidden meaning. If there is bias or delay, what might it conceal? And what might the physics resemble if we allowed our imaginations to roam freely, unburdened by conservatism or caution? Part N, Physics and Engineering Hypotheses. Let us assume, for the sake of argument, that True Atlas is artificial. Setting aside skepticism and conservatism, we must ask, what could it physically be? What engineering principles might explain its acceleration, its luminosity, its color, and its trajectory? This is speculative, but it is informed speculation grounded in physics and constrained by the available data. Let us begin with the concept of a light sail. Light sails are not a purely theoretical construct. They represent a tangible concept proposed by scientists and engineers as a potential method for interstellar travel. The underlying principle is straightforward. Photons possess momentum. When light strikes a reflective surface, it imparts momentum, generating a minuscule yet measurable force. A sail with a large surface area and minimal mass can be propelled by starlight over time, eventually achieving speeds that conventional rockets would require an enormous quantity of fuel to attain. For a light sail to produce the observed acceleration of True Atlas, it would necessitate an appropriate area-to-mass ratio. The object would need to be exceedingly thin, perhaps only micrometers thick, and highly reflective, with an albedo approaching unity. Materials such as aluminized mylar or carbon fiber composites could achieve these specifications. At a distance of 1.36 astronomical units, the intensity of sunlight is diminished compared to Earth's orbit, but it remains sufficiently potent to propel a sufficiently large and lightweight sail. Performing the calculations, radiation pressure at 1.36 astronomical units for a perfectly reflective surface is approximately 4.5 micronewtons per square meter. To achieve an acceleration of 135 kilometers per day squared, which converts to roughly 1.56 times 10 to the power of -4 meters per second squared, a specific area-to-mass ratio is required. If the sail has an area, for instance, of 1 square kilometer and a mass of a few hundred kilograms, the figures begin to align. This describes a thin sail, but not one that is impossibly so. The challenge lies in the fact that such a sail would need to withstand the rigors of interstellar space for potentially millions or billions of years. Cosmic rays, micrometeorites, and interstellar dust would inevitably erode its surface. The sail might be tattered, torn, or partially degraded by the time it reaches our solar system. Such degradation could account for why the object does not behave precisely like an unblemished sail. It might be tumbling, reflecting light asymmetrically, resulting in acceleration vectors that depend on its orientation relative to the sun. Another possibility is an onboard propulsion system. Spacecraft executing gravity-assist maneuvers often engage their engines at perihelion, the point of closest approach to the star or planet, serving as the assist body. Firing the engines at perihelion maximizes the efficiency of the burn because the spacecraft is traveling at its maximum velocity at that juncture, and the Oberth effect amplifies the change in velocity. If 3 Atlas were a spacecraft undertaking a powered gravity assist, it might activate an engine near perihelion to modify its trajectory. What kind of engine? Chemical rockets are improbable. They require propellant, and carrying sufficient propellant for a burn lasting days or weeks would necessitate a substantial mass, inconsistent with the observed acceleration. Electric propulsion, such as ion drives, could be a viable option. Ion drives generate low thrust over extended periods, achieving acceleration gradually but efficiently. However, ion drives require a power source, typically solar panels or nuclear reactors. A spacecraft with a degraded power system might still be capable of low-thrust maneuvers. Alternatively, consider exotic propulsion methods. If the object originates from an advanced civilization, it might employ technologies beyond our current comprehension. Perhaps it manipulates electromagnetic fields. It could utilize some form of reactionless drive, although such drives would contravene the principle of conservation of momentum as we currently understand it. This is highly speculative, bordering on fantasy. However, if we are contemplating the possibility of alien technology, we cannot dismiss technologies that surpass our present scientific understanding. What about the materials? If 3 Atlas is artificial, what is it composed of? Metals would serve to explain the blue coloration and high reflectivity. Aluminum, titanium, or more specialized alloys could possess the requisite strength-to-mass ratios. Carbon composites represent another possibility, being lightweight and robust, capable of enduring harsh environments. Certain materials might exhibit unusual thermal properties, reflecting or emitting light in ways that do not conform to natural objects. Spectroscopic analysis could potentially reveal material signatures. Metals possess characteristic absorption and emission lines. If 3 Atlas reflects sunlight with a spectrum displaying metallic absorption features that would constitute compelling evidence. To date, published spectra have not revealed such features, but the resolution and signal-to-noise ratio of those spectra may not be sufficient to detect faint lines. Thermal infrared observations offer another avenue. If the object possesses an internal heat source, it would radiate more infrared energy than expected for a passive object heated solely by the sun. The James Webb Space Telescope, with its infrared sensitivity, could detect such excess emission. If observations conducted in December reveal thermal anomalies, this would strengthen the hypothesis of artificial origin. There also remains the question of purpose. If 3 Atlas is artificial, why is it here? Is it a probe dispatched to study our solar system? Is it a derelict, a piece of ancient technology long since rendered inoperable? Is it part of a network, a fleet of similar objects dispersed throughout the galaxy, engaged in monitoring or mapping stellar systems? Loeb employed the metaphor of a Trojan horse, suggesting something that appears benign but may harbor concealed payloads or functions. This metaphor is provocative, even ominous, but it warrants consideration. Could the object be deploying smaller probes? Could it be that this object is shedding components as it traverses our solar system? While there's no direct proof of this, the absence of evidence doesn't necessarily confirm absence itself. If such probes are indeed real and small enough, detecting them with our current telescopic capabilities would be exceedingly difficult. Designing an apparatus capable of enduring billions of years in the harshness of interstellar space is a monumental undertaking. The cumulative effects of radiation exposure, extreme temperature fluctuations, and constant bombardment by micrometeoroids would inevitably degrade any materials over vast stretches of time. Any civilization advanced enough to engineer such a device would surely have factored in this degradation, perhaps by building in substantial redundancies or utilizing self-repairing materials. The fact that 3I Atlas, if it is indeed a probe, is still operational strongly suggests either a very recent origin or an exceptionally robust construction. This line of reasoning naturally leads us into the realm of philosophy. If 3I Atlas is indeed artificial and functional, it points to a civilization possessing the capacity for interstellar travel, or, at the very least, the ability to transmit messages across interstellar distances. It implies they have existed for a duration sufficient to dispatch such objects throughout the galaxy. Most significantly, it suggests that we are not alone in the universe. Beyond that, it indicates a potential interest, past or present, in celestial bodies like our solar system. This contemplation opens avenues of thought that extend far beyond mere orbital mechanics and the study of light intensity. Part 10. Implications for philosophical and scientific culture. If 3I Atlas is confirmed to be artificial, what are the broader ramifications? This question transcends the fields of astronomy and our understanding of comets and interstellar visitors. It impacts humanity's place within the cosmos, our very self-perception, and our future potential. Let us begin with a statistical inquiry. The Milky Way galaxy harbors hundreds of billions of stars. A substantial number of these stars host planetary systems. Among these planets, some reside within the habitable zones where liquid water could potentially exist. A fraction of these habitable planets might conceivably develop life. From that subset, a portion could evolve into intelligent life forms. Furthermore, a segment of these intelligent civilizations might develop technology capable of interstellar communication. The Drake equation serves as a framework to formalize this chain of logical progression, although the specific values within its terms remain uncertain. Nevertheless, even conservative estimations imply the existence of numerous technological civilizations within our galaxy. So, where are they all? This is the essence of the Fermi paradox. If intelligent life is indeed commonplace, why have we not encountered any verifiable evidence of it? Why haven't we detected their radio transmissions, monumental constructions like Dyson spheres, or vast fleets of spacecraft? One possible explanation is that our search efforts have been insufficient in scope or focus, or perhaps we've been looking for the wrong indicators. Another hypothesis suggests that intelligent civilizations are either exceedingly rare, have very short lifespans due to self-destruction, or that we are, in fact, alone or nearly so in the galaxy. A third possibility is that they or their artifacts are already present, and we have simply failed to recognize them due to our preconceived notions of what to search for. The confirmation of 3I Atlas as artificial would profoundly shift the balance of this debate. It would indicate that technological remnants are not as scarce as previously assumed. It would suggest that civilizations actively dispatch objects into the galaxy, whether as exploratory probes, deliberate messages, or simply as discarded byproducts of their activities. It would, in essence, provide an answer to the Fermi paradox. They are ubiquitous, and we have simply overlooked them. The search for extraterrestrial intelligence, SETI, has predominantly concentrated on radio and optical signals. Researchers have systematically scanned the heavens for narrowband radio transmissions or laser pulses that might signify intentional communication. However, technological signatures could manifest in diverse forms. Enormous structures like Dyson spheres would create distinctive patterns of starlight obstruction. Industrial byproducts in the atmospheres of exoplanets might be detectable through spectral analysis. Interstellar probes or debris passing through our solar system could exhibit accelerations that cannot be accounted for by gravitational forces alone. Avi Loeb has been a prominent proponent of broadening SETI's scope to encompass the search for tangible artifacts. He has argued for the serious consideration of anomalous objects, advocating for their investigation with the same scientific rigor applied to radio SETI. He contends that dismissing such possibilities outright represents a deficiency in scientific imagination. His detractors argue that he is lowering the evidentiary threshold, readily entertaining extraordinary explanations without adequate supporting data. Both viewpoints possess valid arguments. The tension between them reflects a larger quandary regarding how scientific inquiry should address anomalies. Scientific conservatism plays a vital role in preventing erroneous conclusions and ensuring that claims are thoroughly scrutinized before acceptance. However, this conservatism can also ossify into dogma, fostering an environment where certain questions are deemed off-limits, and researchers who pursue them face marginalization or ridicule. Loeb's willingness to challenge these boundaries and pose uncomfortable questions confronts that conservatism. Whether his hypothesis regarding Three-Eye Atlas proves correct remains to be seen, but his approach has undeniably altered the discourse. What would be the consequences if Three-Eye Atlas were definitively identified as artificial? Policymakers would inevitably become involved. Governments would seek answers. Is it a threat? Is it still active? Is communication possible? Can it be recovered? National security agencies might express interest. The object could be classified, its data restricted, or it might become a focal point for international collaboration, a shared discovery that transcends national boundaries. Funding for astronomy and SETI initiatives would likely experience a significant increase. If one interstellar artifact has been discovered, it implies that others may exist. Telescopes would be redirected to search for similar objects. Proposals for missions to intercept or rendezvous with such entities would be drafted. The scientific community would mobilize with an intensity not seen since the Apollo era. The cultural impact would be profound. Religions, philosophies, and worldviews would all face re-examination. Some religious traditions might readily embrace the discovery, interpreting it as confirmation of a universe teeming with divine creation. Others might struggle with the implications. Philosophers would engage in debates about the significance of humanity if we are not unique. Researchers focusing on existential risks would pose questions. If civilizations dispatch probes, do they also deploy weapons? Is the galaxy a safe place, or are we naive to assume benign intentions? Loeb has previously referenced the dark forest analogy, borrowed from science fiction. This concept posits that the galaxy might be a perilous environment where civilizations conceal themselves to avoid detection by potentially hostile neighbors. If this premise holds true, then discovering evidence of other civilizations represents not merely a scientific milestone, but a potential existential threat. We might inadvertently announce our presence to entities that would prefer our silence. While this is speculative and perhaps overly pessimistic, it is a question worth considering. Potential contact scenarios range from benign to catastrophic. A defunct probe confirms the existence of others, past or present, without posing an immediate danger. An active probe raises questions about intent. A hostile artifact represents a nightmarish scenario, though its likelihood is diminished by the vast distances and timescales involved. Public trust in science and institutions would be tested. If the discovery is managed with transparency, if data is openly shared, and if the investigative process is rigorous and inclusive, it could bolster trust. Conversely, any perceived secrecy or the deliberate management or manipulation of information could deepen public cynicism and distrust. The manner in which we handle the three-eye atlas situation, irrespective of its ultimate nature, will establish precedents for how we approach future anomalies. Before fully venturing into the unknown, let us step back and consider other developments occurring at the forefront of scientific and artificial intelligence research. For Three-Eye Atlas might very well be the harbinger of a new epoch, one where the distinctions between the natural and the artificial, between discovery and detection, and between our current knowledge and what we are about to learn, are blurring at an unprecedented pace. Part 11. A recent cometary event, Comet C 2022 R2 Swan. While Three-Eye Atlas has dominated headlines, another celestial body made a close passage near the Sun in late October of the year 2025. Comet C 2022 R2 Swan, first identified by the Swan instrument aboard the Solar and Heliospheric Observatory, provides a valuable point of comparison. To ascertain whether Three-Eye Atlas exhibits genuine anomalous behavior, a control subject is necessary. A typical comet behaving in predictable ways, allowing for measurement of deviations. Comet Swan approached the Sun on a trajectory that brought it to within approximately 0.88 astronomical units of the Sun, slightly closer than Three-Eye Atlas, yet still beyond Earth's orbital path. As it neared its perihelion, it intensified in brightness, developed a visible coma and tail, and displayed all the characteristic behaviors astronomers anticipate from a sun-grazing comet. Photometric observations meticulously tracked its luminosity over time, revealing a brightness curve that adhered more closely to a conventional power law, with an exponent near -3. Well within the expected range for normal cometary activity. Spectroscopic analysis of Swan detected the presence of water vapor, carbon monoxide, and dust. The rates of gas production were consistent with models for a comet of its estimated size and composition. There were no unexpected findings. The object behaved precisely as cometary physics dictates. Ice sublimates under solar heat, gas jets generate propulsion, dust particles scatter sunlight, and luminosity increases proportionally to the amount of material expelled. A comparison between Swan and Three-Eye Atlas starkly highlights their differences. Swan exhibited robust gas emission, whereas Three-Eye Atlas did not. Swan's brightness curve aligned with conventional models, while Three-Eye Atlas presented a steeper curve. Swan's coloration was typical for comets, whereas Three-Eye Atlas appeared unusually blue. While each of these discrepancies, individually considered, could potentially be attributed to variations in composition, structure, or activity patterns, their collective presence paints a picture of two markedly dissimilar entities. One interpretation suggests that Three-Eye Atlas is simply an extreme example, a comet possessing unusual properties that push the boundaries of what is plausible within natural processes. Comets themselves exhibit considerable diversity. They originate in different regions of protoplanetary disks, accrete varying materials, and undergo distinct thermal histories. Some are rich in water, others in carbon dioxide. Some possess porous, loosely aggregated structures, while others are dense and compact. It is entirely plausible that Three-Eye Atlas represents an extreme manifestation of this natural diversity. Another interpretation posits that the distinctions between Swan and Three-Eye Atlas are not merely quantitative but qualitative. Swan is a comet. Three-Eye Atlas is something else entirely. The lack of significant gas emission despite pronounced acceleration, the atypical brightness curve, and the unusual blue hue could all be indicators of a non-natural origin. This interpretation, while more speculative, is nevertheless consistent with the available data. Lessons learned from monitoring Swan are instrumental in guiding our approach to Three-Eye Atlas. Ground-based observatories meticulously tracked Swan using photometry and spectroscopy, compiling a detailed record of its activity over several weeks. These identical techniques are being applied to 3I Atlas, albeit with the added challenges of its fainter magnitude, greater distance, and reduced activity, all of which complicate observations, increase data noise, and introduce greater uncertainty into conclusions. If Swan behaves normally and 3I Atlas exhibits anomalous traits, this strengthens the argument for 3I Atlas being unusual. Conversely, if Swan also displayed peculiar features, unexpected brightness surges, weak gas emission, or strange coloration, it would suggest that our existing models require a fundamental revision across the board. As it stands, Swan appears typical, which, by contrast, makes 3I Atlas appear more suspicious. The structure of the dust tail offers another avenue for comparison. Swan's tail displayed the classic sunward repulsion, bending away from the sun due to radiation pressure acting on dust particles. The shape and luminosity of the tail were consistent with models describing dust grains of various sizes being propelled by sunlight. Should 3I Atlas develop a similar tail, it would lend support to the natural comet hypothesis. However, if its tail, assuming one develops, exhibits a different appearance, excessively straight, too faint, or overly reflective, that could serve as another clue pointing towards an unusual origin. The activity patterns of comets can vary dramatically. Some comets experience outbursts, characterized by sudden increases in brightness caused by the explosive release of subsurface volatile substances. Others exhibit a steady brightening trend. Some fade rapidly after passing their perihelion, while others remain active for extended periods. Understanding this variability is paramount for accurately interpreting the behavior of 3I Atlas. Does its observed behavior fall within the spectrum of natural variability, or does it extend beyond that range in a manner that necessitates alternative explanations? Spacecraft observations of Swan, if any were undertaken, could provide higher resolution data than ground-based telescopes. Solar observatories such as SOHO or the Parker Solar Probe might have captured images or spectra. Such observations, if they exist and are publicly available, could refine our understanding of typical cometary behavior and establish a crucial benchmark for evaluating 3I Atlas. The fundamental takeaway is this: Swan represents what we expect. It is a textbook example, a comet behaving in accordance with the models we have painstakingly developed over decades of observation and theoretical work. 3I Atlas, on the other hand, does not. It stands out as an outlier, an anomaly, a data point that fails to conform. In the realm of science, outliers are typically either errors, random occurrences, or the nascent seeds of new understanding. Determining which category 3I Atlas belongs to is the critical task ahead. Part 12. A new spectroscopic survey tool. Foremost First Cosmic View. While individual celestial bodies like 3I Atlas capture public attention, the broader endeavor to map the galaxy is progressing through comprehensive, large-scale surveys. Among the most recent instruments deployed for this purpose is the 4-meter multi-object spectroscopic telescope known as PHOMOS-T, which has recently been commissioned and is now producing its initial scientific data. PHOMOS-T is engineered to conduct wide-area spectroscopy, enabling it to capture the spectral signatures of thousands of stars, galaxies, and other celestial objects simultaneously. Spectroscopy serves as the foundational tool in modern astronomy. By dispersing light into its constituent wavelengths, astronomers can ascertain the chemical composition, temperature, density, and motion of distant objects. A single spectrum can reveal whether a star is rich or depleted in heavy elements, whether a galaxy is actively forming stars or in a quiescent state, and whether an object is moving towards or away from us. When this capability is applied across thousands of targets, it begins to construct a detailed panorama of the galaxy's structure, history, and composition. The inaugural data release from FOMOS-T, sometimes referred to as the first cosmic view, encompasses spectra of stars within the Milky Way's disk and halo, galaxies at various redshift values, and other objects of significant interest. The sheer volume of data generated is astounding. Each night of observation yields spectra for thousands of targets. Over the course of months and years, the survey is projected to accumulate millions of spectra, creating an invaluable resource that astronomers will utilize for decades to come. What is the relevance of this to interstellar objects like 3I Atlas? Large-scale surveys significantly enhance our capacity for anomaly detection. When examining a single object, it is challenging to ascertain its uniqueness. There is no established baseline for comparison. However, when observing millions of objects, discernible patterns begin to emerge. This allows for the identification of outliers, objects exhibiting unexpected chemical abundances, peculiar kinematic properties, or unusual spectral characteristics. These outliers are often the most intriguing because they deviate from established models, prompting us to ask novel questions. Hypervelocity stars serve as a prime example. These are stars moving at such extraordinary speeds that they are escaping the galaxy's gravitational pull. Their discovery was facilitated by large-scale surveys that measured the velocities of numerous stars and flagged those exhibiting unusually high speeds. Once identified, hypervelocity stars became subjects of intense investigation. Their origin and the mechanism by which they acquired such immense velocity are key research questions. The prevailing hypothesis suggests they were ejected from the galactic center due to interactions with the supermassive black hole, though other mechanisms remain plausible. Chemically unusual stars represent another category. Most stars possess compositions similar to our Sun, with variations influenced by their formation location and epoch. However, surveys occasionally identify stars with elemental abundances that do not align with any known stellar population. These stars might be relics from the galaxy's early history, or they might have originated in unique formation environments. In either scenario, they offer insights into processes we do not yet fully comprehend. Interstellar objects could be identified by surveys like FOMOS-T through a comparable process. If an object's spectrum does not match any catalogued comet, asteroid, or stellar class, it is flagged for further investigation. Similarly, an object exhibiting unusual motion, moving too rapidly or in an unexpected direction, would be flagged. The greater the number of objects surveyed, the higher the probability of discovering rare, peculiar, or anomalous entities. FOMOS-T also contributes to mapping the structure of the Milky Way. By measuring the chemical abundances and velocities of stars, astronomers can reconstruct the galaxy's evolutionary history, identifying past merger events, stellar migration patterns, and the distribution of different stellar populations. This research provides a fundamental basis for understanding the origins of interstellar objects like 3I Atlas. If we possess knowledge of the kinematics of various stellar populations, we can trace backward, estimating the stellar populations or regions from which an interstellar object might have originated. There is a thematic convergence here. Just as 3I Atlas challenges our understanding of individual celestial bodies, large-scale surveys challenge our comprehension of populations and distributions. Both approaches, the meticulous study of individual anomalies and the statistical analysis of extensive data sets, are indispensable. Surveys are necessary to locate anomalies, and detailed follow-up observations are required to comprehend what makes them anomalous. The future of anomaly detection may involve the integration of artificial intelligence. Machine learning algorithms excel at pattern recognition and the identification of outliers. By training an algorithm on millions of spectra representing typical objects, it can effectively flag those that deviate from the norm. Applying such an algorithm to survey data from FOMOS-T or similar instruments transforms it into a tireless hunter of the unusual, the unexpected, and the potentially revolutionary. Imagine an artificial intelligence system trained on every observed spectrum of every known comet. If presented with the spectrum of 3I Atlas, it could calculate the probability that this object is a naturally occurring comet. If this probability is exceedingly low, the system would flag it for human review. Scaling this process across the entire celestial sphere, encompassing all wavelengths and all types of observations, would create a detection network sensitive to anomalies that might otherwise elude human notice. This is already a reality in other areas of astronomy. Artificial intelligence algorithms have successfully identified novel types of gravitational lenses, pinpointed unusual variable stars, and classified millions of galaxies. Applying these same techniques to the search for interstellar objects or technological signatures represents a logical progression. The primary challenge lies in defining the parameters of what we are searching for. While AI can discern patterns, humans retain the crucial role of determining which patterns are significant. The connection between FOMOS-T and 3I Atlas transcends mere metaphor. If interstellar objects are indeed common, as population models suggest, then wide-area surveys will undoubtedly uncover more of them. Each discovery will contribute to our collective understanding. Each anomaly will refine our models, and eventually we will accumulate sufficient data to definitively determine whether objects like 3I Atlas represent extreme natural phenomena or something else entirely. FOMOS-T is indicative of a broader trend in astronomical research, the transition from targeted observations to comprehensive surveys. Instead of directing telescopes towards specific celestial bodies selected for particular reasons, we are now systematically mapping and cataloging vast swathes of the sky, allowing the data itself to reveal patterns we were previously unaware of. This represents a democratization of discovery, where unexpected findings can emerge from any quadrant of the cosmos. And this leads us to the compelling possibility that 3I Atlas is not an isolated phenomenon. Perhaps it is merely the first in a series. The next generation of surveys may very well uncover dozens or even hundreds of similar objects, each presenting its own unique anomalies and prompting the same perplexing questions. If this scenario unfolds, the ongoing debate will shift from the artificiality of any single object to what the statistical distribution of such findings reveals about the prevalence of technological artifacts within our galaxy. This is a future worth considering, a future contingent on the innovations we are currently developing. Tools such as Foremost, which enhance our capacity to observe, quantify, and comprehend the universe in its full intricacy, are paramount. Part 13. The Draconid Meteor Shower Forecast Industry Modeling for the year 2025. The Draconid outburst is anticipated in October. In October of 2025, Earth will traverse the particulate stream originating from Comet 201 Giacobini-Zinner, giving rise to the yearly Draconid meteor shower. This year's celestial display was predicted to be exceptionally active, potentially reaching outburst levels, a projection based on meticulous analysis of the comet's dispersed material. These forecasts stem from the dedicated work of researchers like Jeremy Vaubalon and Peter Jenniskens, who have devoted years to refining models that explain the evolution and distribution of cometary debris along orbital trajectories. Meteor showers are indeed predictable phenomena. When a comet approaches the Sun, it liberates dust and fragmented matter. This expelled material then spreads along the comet's orbital path, forming a cohesive stream. When Earth's trajectory intersects this stream, the dust particles plunge into our atmosphere at immense velocities, generating friction that causes them to heat up and ignite, creating the luminous streaks we recognize as meteors. The intensity of such a shower is dictated by the quantity of debris shed by the comet, the density of the resultant stream, and the precise geometry of Earth's passage through it. The process of modeling meteor showers necessitates a deep understanding of particulate dynamics. Objects of varying sizes are influenced differently by factors such as solar radiation pressure and gravitational disturbances. Smaller particles are propelled outward by the sun's light, dispersing at a faster rate than their larger counterparts. Over time, the stream naturally disperses, becoming less concentrated but extending over a greater region. By simulating these processes, scientists can accurately predict the timing and location of meteor showers, sometimes with decades of advance notice. The parallels to cometary outgassing and the formation of their characteristic tails are strikingly evident. When one models a meteor shower, the fundamental task is to simulate the movement of dust particles under the combined influence of solar radiation, planetary gravity, and the initial momentum imparted by the comet's gaseous emissions. The identical physical principles apply to celestial bodies such as 3I Atlas. If 3I Atlas is a comet that generates dust, that dust ought to form a tail, reflect solar light, and evolve in predictable patterns governed by the size and composition of its constituent particles. The remarkable success of meteor shower models, where predictions align with actual observations with high precision, serves as compelling evidence that our comprehension of dust dynamics is quite robust, at least for typical cometary material. Consequently, when an object like 3I Atlas deviates from these established models, it warrants thorough investigation. Could its composition be unusual? Is its dust production sporadic? Are there other contributing factors at play? The predictions for the 2025 Draconid outburst were contingent upon particles ejected from comet Giacobini-Zinner during specific close approaches to the Sun in the past. By projecting the trajectories of these particles forward in time while accounting for gravitational influences from planets and the repulsive force of solar radiation, scientists calculated that Earth would encounter a particularly dense segment of the stream. The predicted time frame for this event was remarkably narrow, possibly spanning only a few hours, presenting a challenge for observers but a significant validation for the predictive models. If these predictions proved accurate, and initial reports suggested they were, it underscores the validity of the underlying physics. It demonstrates that when all the forces acting upon dust particles are meticulously considered, the resulting predictions accurately reflect observed reality. This validation is crucial as it instills confidence in applying the same modeling techniques to other celestial objects. However, there is a caveat. Meteor shower models function effectively because the parent comet is well understood. Its orbit, its history of activity, and its composition are known. The models can be calibrated against observations spanning multiple occurrences. In the case of an interstellar object like 3I Atlas, this historical context is absent. We observe it only once as it transits our solar system, forcing us to infer all properties from this singular observation. This significantly complicates the modeling process and introduces greater uncertainty. Furthermore, the completeness of our models is a pertinent question. Are there aspects of dust dynamics that remain poorly understood? Could there be irregularities in the generation or ejection of dust that our current models fail to capture? The modeling of the Draconid outburst, while sophisticated, still relies on assumptions regarding particle size distributions, ejection velocities, and surface characteristics. If these assumptions are inaccurate, the predictions can be imprecise. Some researchers have posited that anomalies in meteor shower activity, such as unexpected peaks or gaps, might signify previously unrecognized processes. Perhaps comets occasionally release bursts of extremely fine dust that disperses more rapidly than theoretical models suggest. Alternatively, surface alterations might influence ejection velocities in ways not currently accounted for. These are active areas of scientific inquiry and are highly relevant to understanding objects like 3I Atlas. The methodological connection lies in the shared reliance on comprehending the motion of small particles under the influence of complex forces. Both meteor shower forecasting and the modeling of cometary activity necessitate detailed numerical simulations and are rigorously tested against observational data. When the models succeed, they bolster our confidence. When they falter, they illuminate gaps in our understanding. 3I Atlas might be revealing such a gap, an area where our models of cometary behavior prove inadequate or require refinement. Alternatively, it could represent something entirely different. If the object is of artificial origin, then dust dynamics models would either be inapplicable or only partially relevant. A rotating light sail or a disintegrating spacecraft could potentially generate brightness fluctuations that resemble dust tails but do not adhere to the same physical principles. Distinguishing between these scenarios demands observational capabilities sensitive enough to resolve intricate details, which is precisely the objective of the forthcoming observation campaigns. The Draconid shower also serves as a potent reminder that the solar system is far from empty. It is replete with debris, dust, and particles shed by comets and asteroids over eons. The vast majority of this material is natural, a relic of the solar system's formation and evolution. Statistically, however, if interstellar objects occasionally pass through, some might also contribute debris. Could fragments of 3I Atlas, assuming it is artificial and undergoing degradation, become incorporated into the interplanetary dust environment? Could future meteor showers possess an interstellar component? These are speculative inquiries, but they are not entirely implausible. If technological civilizations are prevalent throughout the galaxy and routinely dispatch probes, then a fraction of the interplanetary dust could conceivably be artificial in origin. Detecting such material would necessitate novel techniques, new observational strategies, and a willingness to search for previously unimagined signatures. Part 14. AI Technology Story: OpenAI and AMD Hardware Partnership. In late October of 2025, OpenAI revealed a significant collaboration with AMD, securing access to Advanced Graphics Processing Unit (GPU) infrastructure essential for training and deploying extensive artificial intelligence models. This agreement, representing billions of dollars in computing power, underscores the ongoing technological competition in AI development, where access to hardware is as critical as breakthroughs in algorithms. Why is this development significant for astronomy? For the endeavor to discover interstellar objects, and for the crucial question of whether 3I Atlas is a natural or artificial entity? Because computational power has become the new telescope. The greater the computational resources available, the more data can be processed, the more simulations can be executed, and the more patterns can be identified. Artificial intelligence is fundamentally reshaping scientific methodology, with astronomy standing at the vanguard of this transformation. Consider the sheer scale of contemporary astronomical surveys. Observatories such as the Vera Rubin Observatory, upon its operational commencement, will generate terabytes of data nightly. This data will encompass images of billions of stars, galaxies, transient cosmic events, and moving celestial bodies. No human possesses the capacity to examine all this information. Even extensive teams of researchers would be overwhelmed. However, AI can. Machine learning algorithms are capable of scanning images, identifying objects, classifying them, flagging anomalies, and prioritizing targets for further investigation, all in real time. This capability is already in practical use. The Zwicky Transient Facility, for instance, employs AI to identify supernovae, variable stars, and other transient phenomena from its nightly surveys. The AI algorithm processes images, subtracts the light from background stars, and highlights any changes. Human astronomers then review these flagged events, but the AI performs the crucial initial filtering, enabling the management of such voluminous data. Now, let us apply this to the context of interstellar objects. Envision an AI trained on images and spectral data from every comet, asteroid, and meteor ever observed. Such an algorithm would learn to recognize normal characteristics, understand how comets brighten, predict their movements, and analyze their spectral signatures. Upon the detection of a new object, the AI would analyze it and assign an anomaly score. A high score would indicate a probable natural origin, while a low score would trigger a recommendation for detailed follow-up investigation. Such a system could have identified 3I Atlas as anomalous at an earlier stage. It might have detected its unusual brightness curve, its weak gaseous emissions, or its peculiar coloration, thereby issuing an alert before the object reached its closest approach to the Sun. This would have afforded astronomers more time to plan observations, provided greater opportunities to gather data, and improved the likelihood of resolving the mysteries surrounding the object. The partnership between OpenAI and AMD is symptomatic of a broader trend. The industrialization of AI, particularly the training of large models, demands substantial computational resources, and companies are actively competing to secure them. However, the benefits extend beyond commercial applications. Scientific research increasingly relies on these same techniques and infrastructure. Collaborations between technology firms and research institutions are becoming commonplace, accelerating the pace of discovery. Furthermore, the domain of AI-driven simulation, encompassing the modeling of cometary behavior, orbital dynamics, and dust evolution, is significant. All these areas involve complex physics that can be computationally intensive. AI can expedite these simulations, either by learning approximate models that execute more rapidly or by optimizing the numerical methodologies employed in traditional simulations. Increased simulation speed allows for the testing of more scenarios, the exploration of a wider range of parameter spaces, and the evaluation of more hypotheses. Imagine conducting 1,000,000 simulations of cometary outgassing, varying parameters such as composition, structure, rotation rate, and surface properties to identify which combinations yield brightness curves analogous to 3I Atlas. Traditional methods would require months. With AI-accelerated simulations, this could be accomplished in days or even hours. This accelerated pace is critical when attempting to interpret data from an object that is receding from the Sun, fading from view, and offering a limited observational window. AI could also play a role in designing observation campaigns. Given constraints such as telescope availability, object visibility, and scientific objectives, an AI could optimize the observation schedule, prioritizing those activities that maximize the acquisition of crucial information. This scheduling challenge is complex, involving numerous variables and trade-offs, yet it is precisely the kind of problem at which AI excels. A more somber aspect warrants consideration as well. As AI capabilities grow, so too does their opacity. Neural networks trained on vast datasets can generate accurate predictions, but comprehending the rationale behind those predictions is often challenging. If an AI flags 3I Atlas as anomalous, can that assessment be trusted? What if the algorithm is identifying artifacts within the data, biases inherent in the training dataset, or patterns that lack genuine physical significance? This is the challenge of interpretability. Science demands understanding, not merely prediction. If an AI indicates that an object is unusual, scientists need to ascertain the reasons, identify the specific features that triggered the alert, and determine whether those features are real or illusory. The development of interpretable AI systems is an active research frontier and is indispensable for scientific applications. The synergy between AI development and scientific discovery is mutual. AI requires data for training, and science generates immense quantities of it. Science, in turn, needs computational tools to manage this data, and AI provides them. As both fields advance, their interdependence will deepen, and discoveries like that of 3I Atlas will benefit from this collaborative synergy. The future may witness the emergence of AI-powered telescopes, integrated systems capable of real-time observation, analysis, and decision-making. A telescope might detect an anomalous object. An AI would then analyze its characteristics, flag it as potentially artificial, and autonomously schedule follow-up observations with other instruments. Human oversight would remain integral for final decisions and interpretation of results, but the AI would handle the substantial workload of data processing and pattern recognition. This future is closer than one might imagine. It prompts the question, what will we discover when we begin to perceive, not only with our eyes but with our minds, specifically, silicon minds capable of discerning patterns that have long eluded us? Part 15. AI Policy Story, California's New AI Transparency Law. In September of 2025, the state of California enacted landmark legislation poised to influence the future of human-machine interaction. Informally known as the AI Transparency Act, this new law mandates that all artificial intelligence systems engaging with the public, including chatbots, virtual assistants, voice interfaces, and AI-generated media, must clearly identify themselves as non-human. The objective is both simple and profound. No AI should possess the ability to impersonate a human being. Whether interacting with a customer service bot, perusing an AI-generated article, or listening to a synthesized voice, individuals have the right to know that the entity is artificial. Companies that fail to disclose this fact will face fines, penalties, and reputational damage. This legislation represents a legal acknowledgement that in an era saturated with synthetic content, authenticity itself has become a fragile commodity. This law arose from growing public apprehension. The proliferation of deep fakes, AI-generated disinformation, and increasingly human-like digital personas has blurred the demarcation between the real and the artificial. People are finding it progressively difficult to discern the difference, a situation fraught with peril. When one can no longer trust what is seen or heard, the very foundation of a shared reality begins to erode. Nevertheless, the implications of California's AI law extend far beyond social media or political discourse. They touch upon something more fundamental, something central to how society establishes trust, not only with technology, but with science itself. The parallels are indeed striking. Just as we demand transparency from AI systems regarding their nature, we also expect scientific institutions to be forthright about their knowledge and their limitations, particularly when the subject matter involves cosmic phenomena. And this brings us back to Three-Eye Atlas. If this interstellar object proves to be artificial, or if even a shred of credible evidence suggests such a possibility, it will undoubtedly ignite one of the most significant debates in human history. In such a scenario, transparency will transcend mere virtue. It will become an absolute necessity. Every decision made by NASA, every data set released or withheld, every interpretation offered will be subjected to intense scrutiny. The public will demand complete disclosure because trust serves as the fundamental currency in both the technological and scientific realms. When engaging with an AI, one desires assurance of human involvement. When encountering a scientific claim, one seeks confirmation that it is grounded in empirical data rather than mere speculation. Transparency cultivates such trust, while opacity undermines it. In an era where information traverses the globe instantaneously and experts and influencers share the same digital platform, the demand for transparency has never been more acute or more challenging to satisfy. The California law reflects a broader societal anxiety, a fear that reality itself is becoming increasingly indistinct. Deepfake videos can accurately mimic world leaders, fabricate news events, or resurrect the voices of deceased individuals. AI-generated text can be indistinguishable from human writing. Synthetic voices can impersonate anyone with unnerving precision. As the boundaries between truth and fabrication erode, societies risk losing their collective grasp on what is real. Consequently, labeling AI-generated content is not solely an ethical consideration, it is imperative for preserving epistemic stability, the shared conviction that facts remain verifiable. Science, too, is experiencing this seismic shift. When data points diverge from established theories, or when an object like Three-Eye Atlas accelerates in a manner inexplicable by gravity alone, similar questions of authenticity arise. Are we observing a genuine phenomenon, or is it an error or a misinterpretation? Scientific institutions, much like AI companies, face a delicate balancing act. Releasing unverified data prematurely can precipitate chaos, while delaying disclosure for too long allows rumors to fill the void. We have witnessed this dynamic repeatedly, from early reports of gravitational waves to pandemic data releases and controversial UFO disclosures. Transparency is no longer a controlled dissemination. It has become a battlefield, and Three-Eye Atlas currently occupies a prominent position on that front line. If the anomalous acceleration persists, and indeed cannot be explained by outgassing or dust physics, the public will insist on accessing the raw data, the astrometric measurements, the photometric calibrations, the underlying models, and any residual anomalies. They will seek to know who conducted the analysis, how biases were mitigated, and whether independent verification is in progress. In such circumstances, scientific secrecy would become untenable. The imperative for complete transparency would rival any witnessed in modern scientific history. The AI Transparency Act not only mandates disclosure, but also enforces accountability. If an AI system deceives a user, legal recourse is available. If a company employs AI to mislead the public, there are consequences. It establishes a chain of responsibility in a domain that was previously considered a gray area. Could science ever operate under a comparable framework? Could mechanisms of accountability be implemented for institutions that withhold critical data or misrepresent their findings? This is a complex and thorny question. Science is not commerce, and discovery is not regulated in the same manner as consumer protection. The checks and balances inherent in scientific research, peer review, replication, open debate, require time. They are designed to ensure rigor, not speed. However, when an event like 3I Atlas captures global attention, time becomes an exceptionally scarce resource. Information disseminates instantly, and misinterpretations spread even faster. In such an environment, scientific accountability may need to evolve. Some experts have proposed the establishment of independent oversight bodies for extraordinary claims. These would be committees tasked with rapidly evaluating evidence related to technosignatures, unidentified aerial phenomena, UAPs, or interstellar anomalies before they reach the public domain. Analogous to the Intergovernmental Panel on Climate Change, IPCC, such a panel could provide standardized frameworks for evidence assessment, thereby assisting in differentiating credible anomalies from sensationalized claims. However, this approach carries its own set of risks. Oversight can easily devolve into gatekeeping. If every unconventional finding necessitates bureaucratic approval before it can be discussed, open exploration could grind to a halt. Scientists might refrain from sharing preliminary results for fear of reprisal, potentially delaying or losing genuine discoveries. Once again, the equilibrium between openness and responsibility emerges as the defining tension of this era. California's law does more than just alter behavior, it reshapes norms. It signals to society that we expect honesty from our machines. This represents a cultural shift as much as a legal one. Science, too, is defined by its norms, peer review, reproducibility, and skepticism. However, these norms were established in a slower, quieter epoch, an age when discoveries took months to publish and public reactions unfolded in newspapers rather than viral social media posts. Today, a single dataset or an ambiguous graph can explode across social media within minutes. Before peer reviewers have even opened their emails, the world has often formed an opinion. Perhaps it is time for a new norm in scientific transparency, one that bridges expert communication and public understanding. This would not involve the indiscriminate release of raw data, but rather curated transparency, offering clear explanations, real-time updates, and an open acknowledgement of uncertainties. Transparency does not equate to oversharing. It signifies forthrightness regarding what is known, what is unknown, and what steps are being taken to ascertain the truth. When NASA or the International Space Station, ISS, release preliminary data concerning 3I Atlas, they confront a tripartite challenge. The crucial task involves informing authoritative figures, drawing in the general populace, and safeguarding our reputation for trustworthiness. Overloading the discourse with overly technical language causes the public to disengage entirely. Conversely, excessive vagueness opens the door for speculative theories to fill the void. The delicate balance, where clear communication and careful consideration must coexist, proves the most challenging to maintain. This is precisely why the ongoing discourse surrounding artificial intelligence transparency bears such a striking resemblance to the persistent challenges in scientific communication. Both endeavors fundamentally rely on building confidence through open disclosure, and both face the risk of complete failure if that trust is eroded. The recently enacted artificial intelligence legislation grants regulatory bodies the authority to enforce transparency measures. These bodies are now empowered to scrutinize algorithmic processes, mandate the provision of detailed documentation, and impose penalties for non-compliance. A comparable level of oversight is not yet in place for unusual scientific phenomena, although discussions are beginning to emerge. Within the search for extraterrestrial intelligence community, some individuals have privately acknowledged the necessity for established protocols to address anomalies. These would involve predetermined procedures for handling situations where something genuinely inexplicable is discovered. Key questions arise. Who would be responsible for confirming such a discovery? Who would be the initial spokesperson? How would the collected data be rigorously verified and subsequently disseminated? Until this present juncture, these questions have never necessitated serious consideration. However, the case of Oumuamua may represent the inaugural true test. Should the subsequent round of observations reveal persistent non-gravitational acceleration without any discernible gaseous emissions, the scientific community will find itself under intense public scrutiny. Every instance of hesitation, every delay will be interpreted as deliberate concealment. Every official pronouncement will be subjected to meticulous analysis for hidden meanings. The precedent set by California's legislation offers a clear lesson. Transparency must be a proactive measure, not a reactive response. Once confidence dwindles, its restoration becomes an almost insurmountable task. There exists an additional layer to this matter, the emotional dimension. Artificial intelligence transparency regulations are a direct result of public discomfort with being misled, even if the deception is unintentional. Individuals desire to be aware when they are interacting with a non-human entity. This fundamental emotional need for honesty extends equally to how people perceive and respond to scientific institutions. Should NASA or any other official organization ever present evidence of extraterrestrial technology, even if preliminary, the emotional impact on the global population would be profound. People will seek assurances that the evidence is genuine, that it has undergone thorough verification, and that it is not being manipulated or withheld. Science fiction narratives have prepared humanity for the prospect of contact, but not for uncertainty. What if this initial contact is not a clear, unmistakable signal emanating from the cosmos, but rather a subtle anomaly, a glint of metal in a place where it should not be, a faint acceleration curve that defies established physical laws? What if it resembles Oumuamua, neither definitively confirmed nor definitively debunked, perpetually suspended in a state of ambiguity? The genuine challenge will extend beyond merely interpreting the data. It will encompass managing public perception during a period of profound epistemic upheaval. It is perhaps not coincidental that both artificial intelligence and astronomy are grappling with a similar fundamental issue: how to achieve transparency regarding the unknown. Artificial intelligence poses the question, how do we ensure individuals are aware when they are interacting with intelligence that is not human? Astronomy inquires, how do we effectively communicate when we might have detected intelligence that is not human? Both questions point towards the same uncharted territory, the diminishing distinction between the known and the unknowable. Oumuamua, whether it proves to be a comet or a manufactured object, resides precisely on this boundary. The manner in which we approach its investigation, including our analysis, communication, and disclosure of findings, will significantly shape humanity's preparedness for whatever may lie ahead. At this present moment, Oumuamua is receding from view. It is moving away from the sun, its brightness diminishing, gradually re-entering the vastness of interstellar darkness. However, the narrative surrounding it is far from concluded. Upcoming observations from the JUICE mission, the James Webb Space Telescope, and ground-based observatories may yet provide definitive answers or deepen the enigma. As these results become available, the public will be observing not only the data itself, but also the entire process: how it is shared, who undertakes its interpretation, and whether the involved institutions genuinely embody the principles of transparency they advocate. Ultimately, the way we navigate this critical juncture will have implications extending far beyond the realm of astronomy. It will establish a crucial precedent for how humanity confronts all future anomalies and all subsequent moments of cosmic uncertainty. If Oumuamua ultimately proves to be a comet exhibiting peculiar characteristics, the public interest may wane, but the vital lessons learned regarding trust and transparency will endure. Should it, however, be determined to be something else entirely, then the implications will be far-reaching. This would not only alter our understanding of science and the cosmos, but also fundamentally change our perception of ourselves. If Oumuamua is indeed of artificial origin, then humanity's first encounter with extraterrestrial intelligence did not manifest as a radio signal, a broadcast, or a decipherable message. Instead, it arrived as a critical test of our collective integrity, a challenge to our ability to confront the unknown with honesty, openness, and an absence of distortion. It is possible that the first piece of alien technology that humanity ever detects will not solely reveal its creators. It may, in fact, reveal us, our deepest fears, our inherent limitations, and our genuine willingness to embrace the truth, even when that truth feels overwhelmingly immense.